Welcome. In this lecture, we're going to talk about antiderivatives, which are really, in some sense, how we're going to integrate. So let's do our setup first. We're going to start with a function. So f is going to be our function. And I is going to be some interval. So you can picture like this, and maybe I have, right, and maybe it's an interval like this. So this would be A and B, and if it looked like that, then our interval would look like AB, right? And so that's kind of our setup, and then we have our definition. So this is the setup. And then our definition is going to be that an antiderivative of f, so this is an antiderivative, and so this is of our function f on the interval I. So this is of f on I is going to be, so this is a function, and like this, so it's going to be a function f, so that what we have is that, and then we're going to have that what I want to be true of this function f is that if I take its derivative and I apply it to x, this is going to be the same thing as if I did this, so equals f of x. And this is going to work for all, so this is going to work for each or all x in my interval I. Okay. So as long as I'm in my interval, if I take the derivative of the antiderivative, I should get back my original function. Okay? So now let's look at some examples. So examples. So the first one would be the antiderivative of, and here my function is f of x equals cosine of x. Okay. Well, the first thing that we get, so what is a function whose derivative is going to give you cosine of x? Right, it's going to be sine of x. And then let's go ahead and check that. So if I take the derivative, so the derivative with respect to x of, so I want to take the derivative of this and get that. It's a little bit backwards from what you did before. So the derivative of sine of x with respect to x is indeed precisely what I want for it to be, my function cosine of x. Now we could look at this and we could say, wait. Yes, that works, but that's not the only thing that works, right? Because something that we know from last semester is that if I take the derivative of a constant, I get 0. So I could have added a constant to this. And this is actually highlighting why I say an antiderivative instead of the antiderivative, because there are going to be other options, right? So also, I could take, for example, sine of x plus 1. I could take sine of x, maybe I'll do the same ones as I have in my notes. So I have this, maybe I will subtract pi. Maybe I will take sine of x, and then I will get, and I want to write maybe plus e over 2, for example. Okay, so I could do that. I could add any constant and I would still get this, right? Well, then let's look at another circumstance. So what if I want to take the antiderivative of e to the 3x? And this one I'm doing to kind of highlight that we have to be careful in how we do this, because there are rules of differentiation that somehow kind of skew, that things aren't our first guess often. Okay? So we have, so the antiderivative of, so this should be f of x. Let's be consistent with what we have above. So the antiderivative of f of x equals e to the 3x. Okay, now we need some kind of function so that when I take its derivative, I get e to the 3x. And we have to watch out, because our first thought might be, oh, it's going to be e to the 3x. But what happens if I take the derivative of e to the 3x, I get 3e to the 3x because of that chain rule that isn't an option. We always have to use it when we have a composition of functions like this, where 3x is our inside function. So we have to kind of compensate for the fact that the derivative of 3x is going to give us a 3 in the front if we just take e to the 3x, and so we put a 1/3 in the front. So let me show you what I mean. So we get 1/3. So let's be notationally consistent that this is our big F, equals 1/3 e to the 3x. And then we want to go ahead and check that. So if I take the derivative with respect to x of 1/3 e to the 3x, well, what do I get? So this is, and then this is going to make it much easier to see why I put that 1/3 in front, because I get 1/3 times, and then I have to pick up the 3 from the chain rule, so I get 3e to the 3x. Okay, and that equals, perfect, e to the 3x. Just what I wanted. Okay. That's a little bit off the edge there. Let's fix that. So that's going to be exactly what I want. Okay, so yes. Okay. Perfect. So now we say, okay, I again remember that the derivative of a constant is going to be 0. So I could again do exactly what I did up there, right? That's not a problem. So also, well, okay, I can do just like what I did up there. So I would get maybe 1/3 e to the 3x minus 1/2. That's totally okay. I could get 1/3 e to the 3x plus pi over 2. Right, I can do this again where I could add any constant. So then we can ask ourselves, right, the question to ask ourselves then is like, is what I'm observing exactly how they differ? Okay, so how are the different antiderivatives for a function related? So how are the antiderivatives? And the answer is going to be exactly how you think they are. And so let me just kind of, we're going to use this space over here so that we can get this all at one time on one video. And so here are some kind of important facts, also called a theorem. Theorems are not scary objects. Theorems are useful things that other people put a lot of time into proving so that you have them in your toolkit. You just have to learn how to use them properly. Okay, so the first part is just as we saw over there, right? Because if I take the derivative of a constant, I get 0. The first thing I know is that antiderivatives are never unique. Derivatives are never unique. Okay, and they precisely differ by constants, okay? So that's not a coincidence. That's exactly how they all differ from each other. The antiderivatives for a function differ precisely by constants. Okay, so this is where I try to peek through all the writing and talk to you for a moment. This is the best place to peek through. Okay, so what do we have going on here? What is an antiderivative? So now we're doing the opposite of what we did last semester. So now I start with a function which is already my rate of change. I want to kind of go backwards, okay? So now I'm looking for a new function, and I want the derivative of the new function to give me back my original old function, okay? And we did this over here, and one of the things that we observed was that all antiderivatives for a given function differ by a constant, so it works anytime I want to add a constant. At the same time, that's exactly how all the antiderivatives differ from each other. So you just need to find one of them, and then you say, I take this, and then I add all constants. And we'll talk about that in the next lecture, where we talk about generalized antiderivatives, where we're looking at all of the antiderivatives at once by just kind of adding a constant.